In this problem, we have an air standard cycle with variable specific heat assumption, and we are told that it's a closed system. First of all, we have to remember that the entropy change for an ideal gas in a variable specific heat system is given by delta S is equal to S2 naught minus S1 naught minus R ln P2 over P1. Here, S02 and S01 values are found from table A17. Table A17 lists temperatures and S0 values. First of all, we have to draw PV and TS diagrams. Let's see how can we draw different processes on PV and TS diagram. If you are considering a constant volume process, it's going to be a vertical line on our PV diagram. On the TS diagram, it is going to be a slightly curved upwards process. If you are wondering why we draw it like that, you can revise our TS diagrams in chapter 7. We discussed this as entropy change of pure substance. Remember, when we are talking about a air standard cycle, our operating fluid is a gas. So we are talking about far right side of our superheated vapor region. If you're talking about a constant pressure process, we know that it is going to be a horizontal line on PV diagram. On the TS diagram, it is going to be a slightly curved upwards line as shown here. What if it is a constant temperature line? We can easily draw it on our TS diagram, but how about on PV diagram? It is going to be a slightly curved downwards line as shown here. The reason is, in PV diagram, we draw our constant temperature lines as slightly diagonal line on the gas region. If it is a constant entropy line, it is going to be a slightly curved diagonal line on PV diagram. On the TS diagram, it is going to be a vertical line. Now let's try to draw these processes on PV and TS diagram. The first process is going to be a compression process because pressure is increasing. So we should know that the volume is reducing and the pressure is increasing. Since it's a constant entropy line, we can draw it as a diagonal line with a slight curve to it. Process 2 to 3 is a constant volume process. So in our PV diagram, it is going to be a vertical line, and on TS diagram, since it's a constant volume process, we can draw it as a slightly diagonal curved line, and we can mark it as Q in process. Since it's a heat addition process, we can expect it to increase the system pressure. That is why we drew process 2 to 3 as an upward process on PV diagram. Process 3 to 4 is a constant entropy process, and that is going to be a vertical line on our TS diagram, and it's going to be a diagonal line on PV diagram. The vertical line on TS diagram should stop at P equals 100 kilopascal line, and we can recognize this line by drawing constant pressure line that goes through state 1. Finally, our fourth process is going to be process 4 to 1. It's a constant pressure process, so it is going to be a horizontal line on PV diagram, and this process is going to follow P equals 100 kilopascal constant pressure line on TS diagram. We can mark our constant entropy processes as adiabatic processes. Generally, we draw hatched lines to recognize adiabatic processes on PV and TS diagram. The reason is these processes are constant entropy processes, so we know that these processes are also adiabatic and reversible. Now, this is part A, and for part B, we have to calculate W out, and for part C, we have to calculate efficiency. Now let's make a small plan how to do that. So when it comes to W out, we can see on a heat engine, W out can be written in terms of Q in and Q out. This is by simple energy balance, and we have to recognize Q in and Q out. How can we do that? We know that the system is a closed system. So what can we do? We know that process 2 to 3 is a constant volume process, and that is where we will see Q in. Since it's a constant volume process, WB is equal to 0 and Q in should be equal to delta U. This is by simple energy balance for the closed system. Similarly, for process 421, it's a constant pressure process, so WB is not equal to 0, and we can write the energy balance to find out that Q out is equal to delta H. So we can write Q out is equal to H4 minus H1, and to find W out, what we have to do is find U3, U2, H4 and H1. If you cannot understand why did I write this Q in is equal to delta U and Q out is equal to delta H, you can revise chapter 4 where we established the idea of delta H. For part C, we have to calculate the efficiency, and the efficiency is equal to W net divided by Q in. If we find W net, we can easily find efficiency. Now we are going to find these internal energy and enthalpy values. Generally, for this kind of a problem, what you have to do is you have to start from a point of the cycle and find all the properties through the cycle. Now let's start from T1. T1 is equal to 295 Kelvin. So we can find enthalpy and relative pressure on that point. Remember, for an ideal gas, enthalpy is a function of temperature only. And I found these values from table A17. Since process 1 to 2 is a constant entropy process, we can write the relationship between relative pressures and actual pressures. And we can see that PR2 value is going to be 7.841. Using this, we can find U2 and T2 from our table A17. Since T3 is 1500 Kelvin, we can find U3 and PR3 values from table A17, and since process 2 to 3 is a constant volume process, PV over T is a constant. It's an ideal gas. So we can build a relationship between pressure and temperature. So we can write P3 is equal to 1835.6 kilopascal. Again, process 3 to 4 is a constant entropy process. So we can write this relationship for relative pressure ratio and actual pressure ratio. So we can find PR3 value, and using that PR3 value, we can find H4 from table A17 again. Now we have all the internal energy and enthalpy values to find Q in and Q out. Using these Q in and Q out values, we can find W net out. Finally, we have to calculate our efficiency for this system. Efficiency is always desired output divided by required input. So this is our answer for this question.